We present Veera, an ecosystem designed for robot IoT task planning. In Veera, human, robot, and IoT are coherently connected together by a single AR SLAM device. User first spatially planned a task using the AR interface. When finished, he simply puts the authoring device onto the robot and it starts executing the task. Since the robot is guided by the SLAM feature on the authoring device, our system does not require external tracking cameras to realize room-level navigation and interaction for the mobile robot. Now we talk about the authoring interface of Veera. User first selects a nearby available robot. Then define robot path via spatial movement, or hand drawing on the AR interface using curve or segment line. User can register IoT device into the SLAM map by scanning its QR code. Using the edit function, user can partially loop, mirror, or delete the planned task, and drag the handle on the event line to preview the simulation. User can also insert new events into specific location, including preset or condition-triggered timer, non-robotic IoT function, and logic-driven alternative task line. User first defines its trigger condition, then adds navigation path and IoT interaction on the newly created task line. User can touch on the AR view to select from different task lines and use the event line tool to visualize the simulation. All the events are shown as icons on the event line. User can touch on to review its detail, edit, or delete. Our system allows the task to repeat periodically. When the authoring is finished, user can enter the play mode and put the device onto the robot for task execution. During the play mode, user can monitor the task through another smartphone. He can stop the action remotely if anything goes wrong. Our system can also automatically generate video log during the robot execution for process analysis and debugging. Our first use case features SweeperBot for smart floor cleaning. When starting the authoring, the user notices the power LED on the SweeperBot blinking, indicating low battery. Therefore, he first authors the robot to charge the battery for 20 minutes, and then defines the spots and path for the SweeperBot to efficiently clean the paper debris on the floor. Our second use case features TowerBot for automated fabrication. The user wants to fabricate a few DIY objects, each one 3D printed, surface coated, and properly placed. The whole process takes a few hours. To automate the process and have 3 finished parts by the end of the day, he uses V.Ra system to author the robot and wait for the 3D printer to finish printing the current part, pick it up, and start a new printing job on the 3D printer. He then finishes the rest of the task authoring with the painting machine and the sorting box. Before executing on the robot, he uses the repeat function to loop the entire authored task for 3 times, with 1 hour interval for battery charging. Our third use case features WaterBot for daily plant watering. The flower needs watering every day, while the grass only needs water when it's thirsty. To cater the 2 plants with different watering schedule, the user authors a daily repeating task with alternative task lines, handling different scenarios. When executing, the WaterBot first takes care of the flower. Then on its way back, it will check the status of the grass by its moisture sensor to decide whether or not to water it. If its onboard sensor tells that it's running out of water, it will go to the water station to refill its tank, and then go back to the charging station to charge the battery and get ready for the next day. To evaluate our system, we have invited 10 users for a 2-session user study.